Okay, so with that said, let me introduce Tamara Broderick, who is our second speaker. And I guess you can walk around by holding the microphone, something I didn't realize.
Do I need
Yes.
all these additional capabilities? Good morning. Great to see everybody. So today I'll be talking about how in data analyses, there's always some sort of output or. Okay. I guess this one's even better. So there's always some sort of output or decision that we're making at the end of the day, and so there are two things that we might want that are associated with that. One, we might want to get an uncertainty quantification with respect to the data we've seen so far, and two, we might want to know how robust that output or that decision is with respect to our assumptions that we put into the data analysis. And so let me go into a little bit more detail with respect to just a particular example to get us motivated. So microcredit is these small loans to individuals in impoverished areas, and the hope is that these small loans might help bring them out of poverty. And so we've been working with Rachel Meager, who's an economist here at MIT, and she's been analyzing these randomized controlled trials of microcredit at 7 different sites. Each one is in a different country. And again, we're interested in understanding the impact of microcredit. And so at each of these sites, we have these randomized controlled trial data on between 1,000 and tens of thousands of businesses. And there are a lot of different questions that we could be asking here about this data. And I'll just say, one of them, again, for our motivation, is something like, how much does microcredit increase businesses' profits? Is it actually really effective? Is it helping these businesses? And so let's express that in some unknown quantity, some parameter tau. Now, as we perform this data analysis, there are a lot of desiderata that we have. So one such desiderata is we want to share information across sites. So one thing that I could do, recognizing that these are all sort of very different countries, is I could analyze all the data from Mexico, and then completely separately from that, I could analyze all of the data from Ethiopia. And we expect that's probably a bad idea, because what if I have a new site in a new country I haven't seen before? I'm not going to be able to say too much about that. Conversely, I could stick together all of the different businesses and all of the different countries together, but then I'm not recognizing that Mexico is a different country from Ethiopia. It probably behaves pretty differently, and I want to capture that heterogeneity. And so what I want at the end of the day is the ability to say, hey, there's some global microcredit effect that I want to capture, this tau, but at the same time there's some idiosyncraticness about each of these different countries. Now too, when I'm reporting this tau, this microcredit effect, I could say something like, oh, microcredit, it helps US businesses, or it helps businesses in general by something like $1. But we want to know our uncertainty if we're going to make decisions based on that amount. Is it $1 plus or minus 10 US cents, in which case we're pretty certain that that's the value? Or is it $1 plus or minus 100 US dollars, in which case, maybe we're so uncertain about the effect of microcredit that actually it could be hurting people. And we might want to be really careful about making decisions then. Similarly, in this sort of data analysis, in fact, in any data analysis, we're going to be making assumptions. And we want to know, if I had changed those assumptions a little bit, would I have really changed my decisions? Like at the end of the day, I might be sort of deciding, am I going to make microcredit a policy? Is this going to be something that's really widespread? And before I do that, I want to be really confident that under any reasonable assumptions, I might have come to the same decision. And then finally, of course, we want to do this really quickly. This isn't the only data set we have. We might want to move on to a new data set, or we might find that there's actually a more sort of nuanced analysis that we want to do on this data set, and so we want to be able to sort of cycle through this data analysis pretty quickly. And of course, sort of as I've alluded, as I've gone through these desiderata, none of these are specific to microcredit. So this is a motivating example. It's something that we've been working on with Rachel Meager, but of course we want all of this in many of our data analysis. We want to share information across experiments, we want uncertainty relative to our data, and we want robustness quantification relative to our assumptions. And so in general, Bayesian inference is nice because it provides, at least in theory, some of these desiderata. It lets us, via Bayesian hierarchical models, share information across experiments while recognizing that each one can be sort of heterogeneous. And at the same time, it gives us a quantification of uncertainty. But again, this is in theory. In practice, we don't necessarily get this out easily or quickly. And so that's where our method comes in, getting this fast quantification of uncertainty and fast quantification of robustness. And so going forward, I'm going to start by talking about quantification of uncertainty and then move on to quantification of robustness. Okay, so what's nice, again, in theory about Bayesian inference is that it gives us a full joint distribution over all of the unknowns, all of the parameters of our model. So, one of these parameters we discussed already, this sort of microcredit effect, this global microcredit effect. We might have another parameter that represents something like the base profit in all the different countries. And in fact, we have a ton of other parameters in this model. I'm not showing them here because it's hard to display a truly high-dimensional distribution, but there are many, many other unknowns in this particular data analysis example and in general. Now, in theory, Bayesian inference gives us this distribution to represent our knowledge at the end of seeing our data, the end of our data analysis, and it's called the posterior distribution. And what's nice is that it gives us uncertainties in each of the different parameters in a way that's coherent, that's not going to have any contradictions, because it's one giant distribution. Now, what's problematic is that in any complex analysis, any complex modern analysis, we never have access to this exact posterior. We have to approximate it somehow. So what's been really popular for a while now is Markov chain Monte Carlo to make this approximation. And if we run it long enough, it's going to be accurate, but it's often slow in practice. And so people have been turning more and more to variants of variational Bayes, things like mean field variational Bayes, which is, again, desirable because it's so fast, but can be problematic because it can vastly underestimate uncertainty. In fact, it can do this arbitrarily badly. So for instance, even just for this sort of toy distribution that I've shown the contours here, this is the mean field variational Bayes approximation for this distribution. Well, sure, maybe the mean is okay, but the uncertainty here is the width. And so if we look at the width of green versus the width of red, we're clearly vastly underestimating that uncertainty. And so in this direction, we're being overly confident. We're erroneously saying, without actual data to support this, that we're totally sure about the value here. And so if we don't want to do that, we're going to have to do something different. We also don't get estimates of correlation by using this method. And so what we do is we find a correction that we can apply at the end of this to get more accurate uncertainties. And so we use ideas from statistical physics, perturbation ideas, to come up with what is in the end quite a simple formula. So what we're seeing here is we start by running mean field variational Bayes. We get out this V matrix, it's the covariance matrix. It expresses our uncertainty. And then we apply this sort of pre-multiplication by another matrix, which turns out to be a number of different things that we can compute. And we finally get this new, what we call linear response variational Bayes estimate of the uncertainty, which is going to be a better estimate of the uncertainty, as we'll see. And so again, just to emphasize, let's say we apply this to this particular toy example. In this case, we actually recover the exact posterior. And more generally, what we do is we recover an approximation. And so to emphasize, we start with mean field variational Bayes, and then we apply LRVB to get this correction. And so let's see this in practice on this microcredit data that I mentioned. So what I'm going to do is I'm going to plot our LRVB estimates and our MFVB uncertainty estimates versus MCMC to see how it compares. Now, again, the reason that we're not just using MCMC straight, for the whole analysis is that MCMC here takes on the order of 45 minutes, whereas if we do all of mean field variational Bayes, then we apply our linear response correction, and then we calculate a bunch of sensitivity measures I haven't even told you about yet, and we don't take advantage of distributed computing. All of this takes just 58 seconds still. And so what I'm doing here is I'm plotting for every parameter in this particular model, 1 dot for LRVB and 1 dot for MFVB, for the uncertainty estimate. And so if things are on the x equals y line, we're getting them accurately, and if they're below, we're underestimating the uncertainty. And so as we see, sort of as expected, LRVB is getting the uncertainties correctly, and MFVB is underestimating them. And so to see how this could impact a real data analysis, let's say we're looking again at this microcredit effect, tau. And we find that the mean microcredit at the end of the day is about $3 US, and the uncertainty in this effect is about 1.83 US. And so this is, we find that the mean is about 1.68 standard deviations from 0. And so the key point here is if we had used mean field variational Bayes, we would have underestimated the uncertainty, we would have been overconfident, and in fact, we would have said the mean is more than 2 standard deviations from 0. And so if we were making a decision that sort of got triggered when the mean was more than 2 standard deviations from 0, that's when we thought microcredit really had a significant positive effect. We would have erroneously made that decision without support from the data. So we've seen why it's important to quantify uncertainty. Now let's move on to quantifying robustness. So in general, the sort of question that we're asking with robustness is how sensitive are the outputs, the decisions that we're reporting with respect to our assumptions, the assumptions that go into our data analysis. Now, this could mean a lot of things in a lot of different data analyses, but let's focus in particular on a Bayesian analysis. So in a Bayesian analysis, we start with all of our parameters. I'm just showing tau here, but in general, we would do this for all of our parameters. we start with a distribution that represents our state of belief about those parameters. This is the prior distribution. And then we update it according to Bayes' theorem, according to a likelihood, a generative model of the data, to get the posterior distribution that we saw before. And so in general, this posterior will be more peaked because it represents that, we've seen data, we have more precise knowledge about what's going on. But the key thing is, there are a few assumptions that have gone in here. One, I said I could represent all of my beliefs in this distribution to start with, this prior distribution. Well, maybe I can do that, but I don't have enough time. I'm very busy, so in the time that I have, I can kind of narrow it down, but I can't, precisely say one exact distribution. So maybe there are a variety of distributions that fit my desiderata. Or maybe I have a set of beliefs, and you have a set of beliefs, and we both think we're reasonable people, and we think that we should get the same results at the end of the day under our sets of beliefs. Or I have a set of beliefs, and you ask me next week, and I have a slightly different set of beliefs, and we think that we should get the same results under each of those sets of beliefs. And so what we want to say is that when we make these perturbations to our assumptions, that do our analyses really change, or do they stay the same? And actually, we can also ask the same questions about our data generating model, our likelihood, as well. And so it turns out, and I think here it's even more straightforward to see why a perturbation argument might be appropriate. We can have another perturbation argument and come up with an estimator of the sensitivity. We'll call again the LRVB, the linear response estimator of the sensitivity. And I'll just note that this first part of the matrix, in this matrix multiplication, is exactly the LRVB estimator of the uncertainty. So we've sort of already done this computational work. This isn't additional computational work. We just have this additional matrix multiplication. And we get sensitivities in all perturbation directions by doing this. Now, just to check that this is working, let's pick a particular perturbation direction. So maybe we have some hyperparameter or something that we can perturb, just to check against Markov chain Monte Carlo. And again, we find that the sensitivities are on this x equals y line, that we're estimating them accurately. And just as sort of a high-level sort of illustration of why this might affect your analysis, we did this analysis already where we said, oh, we're looking for this microcredit effect, this mean microcredit effect tau, and we found that the mean was sort of less than 2 standard deviations from 0. And so maybe we do this perturbation analysis, we sort of perturb our assumptions, and we find that within a reasonable perturbation, sometimes the mean is greater than 2 standard deviations from 0. Now in this direction, nothing's really affected. We start off with the decision sort of not to go forward. We didn't trigger our, we're going to make this policy decision. But what could really go wrong is if things went in the other direction. Suppose we had started our analysis with some set of assumptions, some prior unlikelihood. We found that the mean was greater than 2 standard deviations from 0, and so we were about to implement some policy based on that. Now we run our perturbation. We find that for other reasonable assumptions that we could have started with, that in fact the mean is sometimes less than 2 standard deviations from 0. And so this is essentially making us more conservative. It's saying, if there are sets of assumptions under which we might not have, pulled this trigger, we might not have made this decision, we didn't feel that the data fully supported this decision, we would go back to, again, the data and maybe say, hey, let's get some more data, or let's think about, are there certain covariates, certain aspects maybe of businesses that make them more likely to benefit from microcredit? Start asking those kinds of questions. So just to recap, so we've introduced this linear response variational Bayes idea to supplement mean field variational Bayes to get this more accurate uncertainty quantification with respect to the data we've seen, and to get this robustness quantification with respect to the assumptions that are going into our data analysis. Also mention, we have some new work that is related to this idea. So here, essentially, what we're trying to do is we're trying to capture key aspects of our Bayesian inference in a fast way. And so in recent work, we've been changing the idea of, instead of modifying the algorithm, which is what we've done here, what if instead we modify the data? What if we run a pre-processing step on the data to get a smaller weighted data set that sort of stands in for our full data? Then we can run things like Markov chain Monte Carlo more quickly. We can run all of these approximate Bayesian algorithms more quickly, and it turns out we can get theoretical guarantees on the quality of inference at the end of the day here. So if you're interested in any of this work in uncertainty quantification, in robustness with respect to your assumptions, or with respect to your data, which I haven't talked about too much here, but we're working on right now, I'd love to chat more about that. And here's some references I'll just mention. So this is linear response with covariance or uncertainty estimation. This is a workshop paper on the robustness quantification. We hope to have the journal paper up on the archive soon. And this is the work on scalable estimation via changing the data rather than the algorithm. Thank you.
questions while we are preparing for the next talk? Mike?
Yeah, I love the LRV. I love the LRVB trick, and I can see it's got lots of room for application. But suppose that there was a registered lobbyist from the MCMC group, and he said it takes 2 years to run, at least 2 years to run one of these experiments from the money enterprise, the microloans. Why do you worry about spending 45 minutes to get the ground truth analysis?
Right. Yeah. No. So I'm with that idea, and so I think ultimately, end of the day, if you want to be absolutely certain you're getting the right thing, what you could do is you could do this as sort of a early set of analyses, sort of just to quickly go through, maybe iterate through a number of models, and then run MCMC to double check. Here are all the details. Let's just run a final sort of single analysis. So 2 things about that. So one, I think that would be a reasonable sort of data pipeline. It's still easier for the analyst. I would say that even though we do have this data, the analyst's time is still a useful commodity. 2, one thing is with some of these very complex models, MCMC will give us the right answer eventually, but we don't know, unfortunately, when we have that answer, although there's some interesting work going forward in that direction. And so there is some issue, even with MCMC, that we might have run it long enough, but we don't necessarily know. So even there's a little bit of a question.
I guess my comment is in follow-up to the previous question. So to help Tamara a little bit, we work with data that is of roughly the same size in terms of data points, except for every measurement is an image of 1 million bits in it, which means that variational approaches take hours, like say 6 to 8 hours to run. And MCMC we've never ever been able to get any reasonable results. So this is very exciting to see that it's possible that we'll get to accurate estimates of uncertainty. So uncertainty is viewed as something that is impossible to get in these data sets. And so,
well, thanks for that even more compelling answer.
Thank the speaker again.